Okay, so welcome to TA9 of Cognitive Robotics. I guess I haven't seen you guys in a year now. It's 2023. So good to see you. Now we're in a full new faculty apparently. So that's some big changes going on here. This is going to be TA9, TA7 and 8 are on ROS. They will be, I'm still working on them. They're evidently quite complicated to organize and make everything understandable. This TA will not cover ROS. We're going to discuss motion planning, which is one of my personal favorite fields in artificial intelligence. It does not include any ROS. We might discuss a bit of ROS next week, but if we do, then I will have the TAs released from week 7 and 8 well in advance to make it easier for everybody. What did I want to say before? We'll discuss homework 2 at the end of the tutorial. I'll do a separate recording for that. I'll give you guys an example for a basic model. And how you might approach the problem in different ways or decide which problems to approach. The whole point of it was to be very free-ended homework, to give you opportunities to be creative, to solve what I consider an interesting problem using advanced AI methods. Of course, everything has its limits, it's technology, so you have to be creative in how you deal with those limits. So that's kind of the point of the assignment. So course homework 1 and 2 are quite long. Homework 3 and 4, which will be only on ROS, will be relatively short. Since we're coming to the end of the semester, I don't want to start loading too much work on you guys. So again, they'll be relatively easy. Just a reminder, you only have to submit 3 homeworks. If you submit 4, you get 5 bonus points on your final grade for the course. In terms of projects, we will discuss this. Erez and I will discuss exactly how we proceed with the projects, but we'll have announcements for you within the next week or so. So today, as we said, we're going to be discussing motion planning. There is a YAML file that I added in the TA folder that you can use to update your Cograb virtual environment with a few more packages that we'll be using today. We're doing some Python scripts, but we can begin without them for now. So one of the problems that we faced earlier in the course was when we discussed task planning, and we realized we could tell a robot to pick up an apple from a table, and it sounds easy, for example. But in real life, the robot has to know how it's going to approach such a problem. How is it actually going to pick up the apple? It's not simple as just telling it to do so. Problems with geometric constraints fall under the category of motion planning. So up until now, we've kind of been ignoring the geometry of our problems, but now we need to consider that robots that exist in the real world, and they're not intelligent from the get-go. They need to be explained. They need us to explain to them what their world is, how can they act in their world, how should they plan in their world, in terms of the geometry of the world. So right now we're going to discuss in this tutorial exact methods for motion planning and some discrete methods, some grid-based methods for motion planning. Next week we'll discuss more motion planning. We'll discuss sampling-based methods, which are my personal favorites. The week after that, we will discuss integrated task and motion planning. So once we learn how to do motion planning, we've already learned task planning. How do we combine these two? And for example, teach a robot how to wash dishes, or how to teach a robot how to cook dinner, which is things that require both knowledge of the geometric world around it and a sense of what tasks need to be completed in what order. The week after that, that'll be the last week of the semester of the course, and we'll discuss reinforcement learning. We'll intro to that. We'll discuss it in the frame of its relevance to planning problems. And that'll conclude the tutorial material for the course. So let's begin. Just a disclaimer. So this TA is heavily based off material from a course called Algorithmic Robot Motion Planning, taught in the computer science faculty by Oren Salzman. Great course, highly recommend it. If you enjoy this TA, definitely take a look into taking that course. Let me turn off the other lights so you can see the screen better. So informally, the motion planning problem is that we have a robot, we have a set of obstacles in our world, and we want to move our robot through this world from a start point to a goal point without colliding with any obstacles. In order to start discussing the algorithms that can actually solve this kind of problem, we have to give a bit of mathematical basis. So we'll very briefly discuss what this means. So let's discuss some spaces. So you guys might have seen already in the lectures, but we have the most basic concept of space for a robot is the workspace. This is the space, the geometric space available in which the robot can actually act. So say, for example, I have a robot with an arm. The workspace is wherever the arm can reach. That's essentially the workspace. Consider the workspace as like us looking at this real world around us. So in XYZ Cartesian coordinates, for example, you might consider that the workspace is defined according to them. Unfortunately, though, we can't just tell a robot arm to move to point XYZ because robot arms don't really function that way. They have motors, and the motors have to rotate a certain angle to translate linearly. And so it's not as simple as just telling a robot to move to point XYZ. We need to first tell it, well, what should the values at the joints be? What angle should it rotate among its many joints in order to reach desired XYZ position? So this problem is called inverse kinematics. We want to know what joint values do we need to get to a certain point. We're not going to discuss inverse kinematics, but you should have seen it in the lecture I think last week. But given that there is a space of a value of values for the joints in a robot's arm, for example, that will essentially be a free space. It'll be a space in which the robot can turn its arms, in which it will not collide with anything. And instead of defining that space in Cartesian coordinates, for example, X, Y, Z, we can define that space according to the actual ranges of those joint values. So the configuration space is another geometric space that does exactly that. It says, it kind of gives us hints as to whether two joint values or more. For example, if I have a robot that has two joints and each of them is rotating, it's a revolute joint. It tells me that if I set, for example, the value of joint 1, 2, theta 1 and theta 2 over here, then I'll be in this white space. I'll be at this point, and that's not colliding with anything. But if I move it slightly over, if I change the value of theta 1, for example, I increase it, I'll hit some obstacle. So this is a way to represent kind of in the robot's frame of, say, intelligence. We can give it an idea of what's actually around it. Now, I'm sure most of you look from the workspace to the C-space, and you can see the colors are matching the objects themselves. But you might say that it looks quite complicated to actually transfer between them. And this is one of the more difficult parts of planning within the C-space, but it's quite difficult to go from looking at some workspace and translating it to the C-space. For today, we're going to ignore this problem. We're going to consider it simple, but this is just a general constraint of planning of AI, that sometimes it's kind of hard to go from having a clear workspace to having a C-space like this. One important thing to note is that the dimensionality of the C-space is equal to the number of degrees of freedom of the robot. So if a robot has 2 degrees of freedom and has 2 revolute joints, for example, then this is how its C-space might look. It'll have 2 theta values, it'll have 2 degrees of freedom, and thus the dimensionality of the C-space is 2. The workspace can be different dimensionality from the C-space. They don't necessarily have to be the same. And the free space, which is the part that we like the most because it means no collisions, that's all this white area. That's the space where the robot is not colliding with anything. And it's defined in the C-space. So it's the set of values for the degrees of freedom of the robot, for the joint values, for example, that ensure that it doesn't collide with anything. With these mathematical concepts in mind, we can now give a formal definition to the robot motion planning problem. So we have a robotic system with d degrees of freedom. Moving in a known environment, we're only going to discuss known environments today, no uncertainty. And this environment, of course, has obstacles. We know that we have the robot starting at some point S, we wanted to get it to some target point T, and we need to decide whether there's a collision-free path that's continuous between points S and T. So that's the formal definition. This path, of course, has to be in the free space only, because it has to be collision-free. Let me close this. So we're going to discuss today some algorithms that will try and attempt to solve this problem for various cases. But in order to evaluate the actual utility of such algorithms, we can think of some core concepts. We've already seen completeness, optimality, and efficiency before. So completeness, we want our algorithm to be able to find a solution if one exists for every time we run it. This is not always the case with every algorithm. We saw this notion back in TA number 3, but this will be an important concept for us here. Same with optimality. So it's not enough just to solve the motion planning problem. You might have a very wonky way to get somewhere. For example, if I want to go from the Asmacha dorms to the mechanical engineering faculty, I could take the whole loop around, or I could go straight. It's not enough to just go take a whole loop around, because obviously this is super inefficient in terms of energy. So what we'll look for algorithms that are optimal, that find us the best path possible between 2 points. We also want to consider speed, efficiency. So we don't want our computers running forever. We need to have time complexities that are reasonable for us. So this is an important consideration. Generality. So we want algorithms that can solve every case. It can solve a motion planning problem in as large a variety of cases as possible, and not in simple, small cases, because that's not as useful for us. So consider that. And memory footprint, which is a bit less important, but of course, computers are finite, they have finite storage, and we don't want to overload them if we don't have to. There are some things related to the motion planning problem that are going to be well beyond the scope of this course. For example, if I have multiple robots that are working in tandem to move between locations, this is called multi-agent pathfinding. There are other courses at Technion on this. For example, next semester we have the seminar on robotics that will cover this topic, also taught by Oren Solomon. So if you're interested in that kind of stuff, feel free to look into it. Uncertainty, so motion planning in certain environments. So today we're going to talk about environments where we know where every obstacle is, we know where the robot starts, we know where it's going to end, and this simplifies things for sure. But in the real world, this is not always the case. There can always be uncertainty. We might not know everything about our environment, and so we'll need something called belief space planning, and this is covered in the aerospace faculty and Vadim Indelman's course. One last thing is, today we're going to discuss only holonomic robots. We're not going to discuss non-holonomic robots. What that means is that we're going to discuss robots that can control every degree of freedom that they have. So for example, a Roomba has 3 degrees of freedom. It has translation in 2 directions, and has rotation. The Roomba can do all those things. It can move straight, it can move to the side, it can turn. Yeah, there's no problems in terms of its control over its degrees of freedom. A car, for example, is non-holonomic, because a car can only drive forward. It can turn its tires, but it can't move directly to the left. So if I want to plan a path for a car, I can't just plan that it's driving and all of a sudden I parallel park immediately with a sharp turn. I'd have to plan it in. That's a non-holonomic constraint, whereas a Roomba might just go straight, turn, go in. So we'll stick with the easier case. This is just an example of a multi-agent pathfinding problem. They're very interesting problems, and the animations are always pretty cool to look at. So this is just one example. But let's see if there are ways to solve this problem analytically. So the geometry of the space is known. You'd think there should be some way to easily find the shortest path in space. So it turns out that solving the motion planning problem exactly is way more difficult than you'd think. For small numbers of degrees of freedom, you can solve it relatively efficiently. So usually in 2D, 3D space, up to 4D space, we can solve the motion planning problem with relatively good efficiency. Beyond that, it starts to go crazy. The time it takes to solve a motion planning problem grows exponentially with the numbers of degrees of freedom and with the complexity of your workspace. So solving things exactly and geometrically in higher dimensions is not really possible. That's why we're going to limit our discussions today only to, for now, 2D, and we'll suffice with that. The approach for solving motion planning problem geometrically is that we'll look at the free space, we'll kind of break it up into different cells, we'll use those cells to create a graph, and we'll run a pathfinding algorithm over that graph. So there are a few ways to break up the space intelligently. We'll discuss 2 of them. One of them is trapezoidal decomposition, another one is visibility graphs. So let's say this is my C space. We're not going to discuss cases where the C space and the workspace are different, just because it's beyond the scope of the course. Let's assume that we have a point robot. The robot is infinitesimally small, and so it can go anywhere on this map. say this is the workspace and go anywhere, C space will look exactly the same. It's just a translating robot. So moving XY coordinates, you can go anywhere here, and it's infinitesimally small. So any collision will only occur if it hits the boundary of these shapes. So looking at this C space, we have red obstacle, we have white free space. So we're going to look at this free space, and we're going to think, how can we partition it intelligently so that we can turn it into a graph, and then solve that graph relatively efficiently to find a path between 2 points. So first, we'll draw a bunch of vertical lines. We'll start partitioning the free space. Every vertical line we draw will cross through a vertex of one of the obstacles. An important thing to note is that here the obstacles must be polygonal, and curvy or anything kind of fails in those cases. So every vertical line has to pass through a vertex. And we only really care about the free space, so we don't really need to consider, for example, lines inside obstacles. We'll throw them out. We'll throw out other lines like this one, for example, that don't go through vertices anymore. And this leaves us with our partition of space. And now I see I have a bunch of trapezoids, all use white trapezoids, and I partition my space among them. The good thing about these trapezoids is that I know that any 2 points inside one trapezoid will necessarily have a collision-free path between them. So if I have 2 points here and here, any path that I want to draw there, but there has to exist a path, that's collision-free between them. This is because trapezoids are what's called a convex polygon. That just by definition means that any 2 points inside them will necessarily have a straight line path that doesn't collide with obstacles, that doesn't exit the shape. Okay, so we've drawn all these polygons, but what are we actually going to do with them? Slow today. So with these polygons at hand, these trapezoids at hand, what we can do is we can start adding nodes. We can start building the graph out of the trapezoids. So first, we'll add a node at the center of every single trapezoid. So we'll take the geometric center of this is a rectangle, so it's easy to see where it is. But we'll just take the geometric center of every single trapezoid and add a node there. Next, what we'll do is we'll add a node at the midpoint of every line segment of the trapezoid. So all these line segments will add midpoints wherever. Finally, because the midpoint, the center point, and this edge point are technically within the same trapezoid, we know that if we draw a straight line between them, there'll be no collisions. If we connect every trapezoid center point to the edge points, we know that we're going to receive a graph with no collisions at all. We don't have to do any collision checking. We automatically know that we have collision-free paths. One of the biggest problems in motion planning is collision checking. It's extraordinarily computationally expensive. Not extraordinarily, but it's very, very computationally expensive. And it's one of the biggest costs of many motion planning algorithms. So the boon here is that we don't even have to do it because we can use the unique properties of trapezoids. Now here I've finished the pre-processing phase. I haven't even said anything about the robot. I haven't said where it starts, where it wants to go. I've looked at the workspace, the C space, and I've turned it into a trapezoidal map. This is the trapezoidal map, also called a road map, or a graph, whatever you want to call it. And our next step, of course, is to add the start and goal point. So let's say the start here, the goal is there. I'll add the start and the goal to the graph by connecting those points to the center of the trapezoid in which they exist. So luckily, identifying in which trapezoid a point exists is relatively easy. So we know we can find where this P star is, which trapezoid it is. And once we know where it is, we can connect it straight to the center of that trapezoid. And again, because trapezoids are convex, there will be no collisions between this point and that point. So we can easily add them. Again, no collision checking at all. Once we have the start and the goal point attached to the graph, boom, we have a graph with one start point, one end point, and we can easily employ a path finding algorithm such as Dijkstra, such as A star, that'll very efficiently solve this problem. So you see here, we found a path from the start to the goal. That's collision free. We haven't had to do any collision checking. We know that it's completely in free space. Now, what's the drawback of this algorithm? We know that we can see that it's complete. We can imagine that it's complete for polygonal obstacles. But you can see by yourself that this is by no means an optimal path. We've traversed through the centers and the edges of trapezoids, and that says nothing about how good this path is going to be. I think that there's a better path that goes just like that curves even more. So that's one limitation of a method like this, is that we won't be able to get an optimal path from this because it's going through these straight line segments and it's ignoring the fact that we can get much closer to the obstacles. How do we reconcile this? So this is where visibility graphs come in. So let's give a little bit of intuition. So if I want to look at an optimal path between a start and a goal point, again, we'll assume that we're in a world where it's 2D, we have a point robot, it's translating in space, and what's the last thing? And then all the obstacles are polygonal, which is important for this. We can imagine that we might take some rubber band, take it between the start and goal point, and let it loose and see what it sticks to. So immediately you can see that, like, for example, the little rubber band method, I let it go, the red will probably go much closer to this vertex, it'll hold around this vertex, and it'll get to the goal. And it maybe shouldn't take too much convincing to see that this is the optimal goal in this problem between those 2 points. So this is some intuition for how exactly we're going to use this algorithm. So what we're going to do is we're going to look at a problem. For example, we have this green is the start, that red's the goal. We have 2 obstacles that are polygonal, they're both brown. What we'll do here is we will take all of the vertices of these polygons, we'll add them to a new graph that we'll call a visibility graph. And what we'll do is that for every single pair of points, for every single pair of vertices on these polygons, we'll draw a straight line between them and see whether or not that intersects any of the obstacles. So for example, if I look at these 2 points, I see that I can draw a straight line between them without any collisions. Whereas if I try and draw, for example, a straight line between this one and this one, I see that it goes right through the obstacle. I don't care about it. So I'm only going to add these kind of edges. These are called visibility edges. These are vertices which are mutually visible. They can see each other straight. There's nothing blocking them. Imagine if I'm looking from here, there's no way I can see this vertex. So that's why they're called mutually visible or mutually invisible. Once I do this for every single set of vertices in the of all the obstacles in the C space, what I'm going to get is a nice little graph. With this graph at hand, I can then consider looking at the start and the goal point. I'll add them as well to the same method. I'll look for the goal node. I'll look for every single vertex here. I'll see whether or not it can actually see that vertex. So it can clearly see this one and this one, but of course it can't see that. That's how I'm going to add it to this visibility graph. And this here is the final product. This is the graph that we're going to solve in the end. Again, you can imagine that we can easily apply Dijkstra or A star to this graph and find some solution between the start and the goal. What's great about this algorithm is that it actually allows us to find the optimal path between 2 points. So if I use Dijkstra will return the shortest path between 2 points. Guaranteed, that's the point of the algorithm. If we run it on this graph, we'll get this solution, for example, and you should be able to convince yourself that this is the optimal path between the green and the red point. There is no better path than this in this space.
You mean the shortest, right?
Yeah, shortest path. I'm defining optimality in terms of distance, Euclidean distance being my cost metric. So we'll discuss Euclidean distance only, no other metrics. So this is, again, a nice method. We get an optimal algorithm, a complete algorithm that is, what I want to say, optimal and complete. It's a bit more computationally expensive than doing the trapezoidal maps. As you can imagine, optimal algorithms are usually more expensive. So because we have to consider collisions here, this increases the computational cost of this. So I have to consider whether these 2 points collide. And even worse, I have to do it between every pair of points. So I'm taking n points, n vertices in my graph. I have to do n squared iterations to check every single pair of points, and then I have to do collision checking between those points, which is even more. The complexity goes up to, I think, n to the third. In this case, it goes up to n to the third. We can do it a bit smarter and get to n squared log n, but still, this is quite rough if we want to have environments with larger obstacles, with a lot of obstacles, with a lot more complexity. So that's one of the main drawbacks of this kind of algorithm. Whereas if we go back to trapezoidal maps, I think I glossed over it a bit, but we can build a trapezoidal map in n log n time and not n squared log n time. So it's a bit faster, but again, it doesn't guarantee optimality. So that's, again, the cost versus quality trade-off that we have to deal with these kind of algorithms. So there should be some code here. So yeah, so I put in this homework, in this TA, sorry, a code implementation of visibility graphs based on an assignment from the robot motion planning course here at Technion. To use this code, you just need to run this line, pip install map plotlib shapely heaptict. These are three libraries that are used here. You can either run this line, or if you're working in virtual environments, you can update your environment using the YAML file that I've attached inside the tutorial, either one. The versions don't really matter for those three. Add whatever versions, there's no issues there. So that we have that, let's import the necessary modules. You'll see that the modules for this code sit in this visibility graph folder. So there's Dijkstra, there's visgraph. These are the two Python files that contain the code. Give it a second to run. So first, you can look at this a bit more in depth later. I just want to get through the TA, but this is how I'm going to define where's my robot in space, where do I want it to go, and what are the obstacles. So taking a look, we can see this is how the C space is going to look. So again, we're talking about a point robot that translates in space. So its C space and its workspace are identical, looks in 2D. So that's why we have this graph, and this is the only graph we're going to consider. All these algorithms, by the way, work in the C space. So if I have a workspace that's different from my C space, I have to consider the effects of that. But for today, at least, we're going to kind of gloss over that. So looking at this problem, let's see how I can start building my visibility graph. So like we said before, every edge of every polygon, every obstacle, I'm going to look and see which other vertices it can see in space. And this builds me my visibility graph. And once my computer starts working, we can add the start point and end point to the graph. We can again find all mutually visible vertices in workspace of all the obstacles. And we apply something like Dijkstra. In this case, it's Dijkstra. Or we can do ASAR or any other optimal path planning graph search algorithm. And we'll get the optimal solutions. This, again, is the shortest possible path between this start point and that goal point. One important thing to note is that here the robot technically is touching the edges of the obstacles. So this is an important consideration for here. In order to make the algorithm optimal, we have to consider that the robot can technically touch the vertices. So they're, I think it's a closed set. Yeah, something has to do with set theory. But the point is that we'll assume that we can get infinitesimally close to the vertex such that this is a valid path. Okay, so these approaches worked for polygonal obstacles, but this isn't always the case. We might have a bunch of toilet paper rolls. These are of course not polygons, and these might block our path, and we cannot use, they don't have any vertices, so we won't be able to use the methods above. So one thing we can do is we can now ignore the geometry of the free space. So we've just discussed geometric methods. Now we're going to move to something called grid-based approaches. So we'll ignore again the geometry of the free space. And what we're going to do is we're just going to put a grid over our C space. We're discretizing the C space and specifically the free space, such that it doesn't matter what the shape of the obstacles are. We can find some path between the start and the goal point along this grid. So I've put some C space here. I've added a grid of certain resolution. So resolution just means how fine, how small, or how big are the blocks in the grid. As you can see, if I just follow a path like this, I just go along these lines, I'll easily get from the start to the goal. So in this case, luckily I have polygonal obstacles that happen to fall on the edges of the grid. The vertices fall on the grid points, and the start and the goal are on the grid. So it'll be easy to just find a path between them with no trouble using something like A star. In this case, A star is going to be used, and we'll see it soon in the implementation of it. You can already see that this again isn't optimal. Already here, we didn't find an optimal path, because we could have definitely gotten closer. This is because we discretized the space and we've limited ourselves to move in 4 directions. We only go up, down, left, right. Of course, we can add more freedom, so we can go 45 degrees each direction. We can do 8 direction planning. Of course, you can imagine that the more directions we add, the more complexity there is in our algorithm. So we can't just have it go to any angle, because that would definitely increase the complexity of our algorithm. But there are algorithms that kind of deal with how you could approach that. So, for example, there's any angle A star, which is an incremental algorithm that allows us to plan using a more fine set of angles, and not just these 4 directions or 8 directions. So again, even if I add these diagonal terms, I still don't get the optimal solution. I get a much closer solution. Am I guaranteed to get a solution every time? Is this complete? The answer is no. Grid-based approaches are not complete approaches for all resolutions. So you can imagine that I might run into trouble if I have, for example, 2 obstacles like this. I have obstacles in the space, and there's a very narrow passage between them that would allow me to get from the goal from the start to the goal. The problem here lies in that if I define my grid too big, there's just no way for me to cross the points of the grid and pass through this passage without colliding with anything. So in this case, I've chosen a resolution that's too large. I cannot guarantee that my algorithm will return a solution between the start and the goal. So this is not complete. Of course, you might think that we can just make the grid as small as possible. But the more resolution, the smaller resolution we have for our grid, the more vertices in our grid, the more vertices in our grid, the more vertices in the graph, and the more vertices in the graph, the computational complexity increases dramatically, and it makes it infeasible to have too small of a resolution. So there is a lower bound to what we need to do, what we need to make our resolution in order to guarantee a solution. So we'll define a notion called clearance. So clearance is the minimum distance between some path and an obstacle along that path. So if I have, for example, I live in a blue path, well, I see that the closest obstacle it gets to is over here at some distance d between the path and this obstacle. And this is the smallest distance between the path and some obstacle. Everywhere else, you see that it's fine. It passes through. So this notion of clearance will help us understand what resolution we need for our grid. So we can set the lower bounds to being that the clearance should be greater than h over square root 2. I'm not going to put the proof here. But if we apply that, we see that we see that we get a resolution small enough, and now the grid search will work. I'll have a path along my grid that goes from the start to the goal, and all is good, and I am guaranteed to get a solution if one exists in this case. Just one other thing to consider with these methods is that grid-based approaches do not scale well with dimensionality. So this is a 2D example, but if I go to 3D, if I go to 4D, and so on, think that I'm taking a 2D grid and turning it to a 3D grid, and then to a 4D grid, and this exponentially increases the number of vertices and makes this kind of method very, very infeasible at high dimensionalities, at high numbers of degrees of freedom. So if I have a 6-stop robot, for example, I'm not going to use a grid-based approach. So let's look at a code implementation just for the 2D case. So again, it's here in this grid-based search folder. There should be 2 Python files here and a map file. The map file just allows me to draw the map. So let's look at the actual problem at hand. So I have a robot that starts at the thread point and wants to finish at the screen point, and there's this yellow obstacle around it. And I have the free space is purple. So this is my C space again. It's a point robot translating in 2D. So the C space and the workspace are identical. Now in this case, I'm going to use a discrete approach, a grid-based approach, in order to plan a path from the start to the goal. So let's run the next cells. We're going to use A star in this case. So I'm going to discretize my grid, discretize my free space, sorry, turn it into a graph, and then run A star on that graph. So let's see what that looks like. So I've discretized it in some way where I think it's 3 grid points between every 2 X marks. So in this case, I've discretized. You can see that there is some uniform look to how these points are set up. The robot can go between any of these points. And I see that I've used A star to plan. Well, A star can also do 45-degree angles, as we mentioned before. And this is the path that A star chooses. So it's not optimal. We see that if we want an optimal solution, we have to go from that point to this edge to that edge straight, and we can do that with a visibility graph. But this is just an example to show you we can use grid-based approaches in cases where it's not so straightforward, such as non-polygonal obstacles. So that's it for today. Luckily, we finished on time. Next week, we're going to continue discussing motion planning. We're going to go over sampling-based methods. So as we said, most of these methods don't really scale well. If we increase the DOFs, we have a more complex workspace with weirder obstacles. So there are sampling-based methods that can actually help us approach this problem. They're going to be probabilistic. It's not going to be deterministic in the same way as these algorithms are, but it's going to help us scale our motion planning algorithms to higher dimensions. So that'll be next week. Hopefully, if I can get those ROS tutorials out for you in time, then we'll also look a bit at MoveIt, which is a software package used with ROS for motion planning. So that'll be a nice thing there. For now, I'm going to stop this recording. I'm going to now shift to discussing homework number 2. So let me just stop sharing, stop the recording.